Hello and welcome to today's Military and Aerospace Electronics web chat. Getting ahead of AI processing requirements with an AI-ready system architecture for MOSA development, sponsored by Elma Electronic. I am Jamie Whitney, Senior Editor of M&AE with Endeavor Business Media. To begin, let me explain how you can participate in today's presentation. First, if you have any technical difficulties during today's session, please submit to the questions window and our technical experts will help you out. We recommend disabling any pop-up blocking software or extensions in your browser, as these can cause issues with the webinar player. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of the screen and hit the submit button. To refer a colleague to today's discussion, share it on social media, or access event resources, click the icons on the left rail of your screen. Also, please be aware that today's session is being recorded and will be available on the M&AE website within the next 24 hours. You'll be notified by email when the archive is available. Now, I would like to introduce our panelists for today's discussion. Ken Grobe, Director of Embedded Computing Architectures at Elma Electronic. Chris Fadley, Chief Technology Officer at EIZO Rugged Solutions. And Nigel Forrester, Director of Product Strategy at Concurrent Technologies. Thank you all for joining us, and let's get started. Ken?
Thanks, Jamie. Well, I get a little bouncing here. So today we're here to discuss getting ahead of AI requirements and how you might implement them with an AI-ready architecture for MOSA development, and in this case, specifically SOSA. So a few topic points by way of introduction. First, we'll talk about what we mean by what is AI-ready, look at SOSA profile reviews that are applicable to AI systems, how the expansion plane can be used and is used in building AI processing elements, some discussion about scaling, some kind of exciting news about new GPGPUs available from EIZO that help us solve these problems, and also an SBC technology overview that will be presented by Nigel of Concurrent. And then lastly, some topologies to support development and test. So what are some of the considerations for an AI-ready development platform? When we take a look at this, we need to make use of SBCs, single board computers, and pair them with GPGPUs, and then also potentially have other plug-in capability or other plug-in card slot capability in the system. In SOSA, boards are called PICs, or plug-in cards, and these are the actual cards that we use to build out a platform using these modules that are based on OpenVPX. The development platform also needs to be flexible in that it needs to be aligned specifically to AI hardware and the architecture around that hardware. If we look at user-specific applications, some of them might be in today's world around sensors, ISR, EW, the ability to run inference models, and then algorithms that drive these applications that define the data sets and the use case around that data. These use cases drive the need for the system topology. SBCs, there's a couple of choices. There's the IO specific, which is a profile type, and compute intensive. So we'll look at how we compare those with GPGPUs. And then with respect to GPGPUs, as technology moves forward, we have more choices relative to feature set in the GPGPU and how it's connected to solve applications that involve sensors. Lastly, to couple these things, we need to look at how the expansion plane, or PCIe, is used. So taking a look at trends, GPGPUs are moving rapidly, driven by NVIDIA, and we see two new architectures coming towards us, Ada Lovelace and Blackwell. Blackwell being just recently introduced and quite capable. If we look at applications that we've built from prior architectures like Ampere. This is an example of one where we have an inference model running across two cards that's doing object detection. And this is just one of the capabilities that you can implement in this rugged form factor. So again, looking at what types of applications are feasible to run on AI elements in computing demos that can be ruggedized. From NVIDIA, we've stood up applications that are shown here, including synthetic aperture radar, SDR, software-defined radio, with, in this case, the ability to do text or speech to text translation, and actually run a language model to convert languages from one language to another. And then a geospatial application is shown here on the right. If we look at software that's required to do this, we have a stack that's been shown, that's been actually done by NVIDIA. And this shows us a set of technologies that are available that sit on top of the hardware that we need to put together to implement AI capability. As we saw before, the applications are things like geospatial, SAW, radar, SDR, comms, LiDAR, and a number of others. And the tool sets that we have are shown in the green blocks that include CUDA libraries, AR tensor processing, Holoscan that Chris Fidley will talk about later, Rapids, CUDA, DACA, and then streaming pipeline APIs. So to break this down, this slide shows a set of building blocks to implement AI capabilities. On the left, we have one of the key elements, which is the Intel-based processor that must be present to drive the GPGPUs and implement the software within the system. In today's example, these are cards from Concurrent, and we'll look at how these have evolved with much greater capability in the memory and processing areas, and Nigel will address that towards the end of the presentation. In the middle of this, we have the platform itself. In this case, this is the development platform, and in Elma's parlance, we call this a compact frame. And it's enabled by a topology, which is composed of profiles that are connected together to implement a backplane. And on the right side, we have the building block, which is the GPGPU PIC or plug-in card, of which there's several choices, and Chris Fedley will explain details about this as we go through the presentation. So in applying GPGPUs, what do we need to consider relative to these accelerate, the GPGPU and the processor? In SOSA, there are applicable profiles. They're limited to promote interoperability, but still cover the necessary interfaces that we need to use. So we have to use these profiles in an appropriate way to implement a topology to be able to affect an AI capability. In doing so, we have applicable SBCs and applicable GPUs. They come in sort of different configurations. So the topology will consider the speed, how fast the lanes are, the width, and then the protocol for communication. In today's terms, we can develop backplanes that are capable of 25 gigs per lane, which increases bandwidth. It allows us to implement control and data plane architecture, and it also allows us to develop a topology that can support multiple GPGPUs. So in looking at these, we have here the four main groups that we need. The SBC profile, which comes in two flavors. In one case, we use something called the standard payload profile, or 14.6.11 in a short form within OpenVPX. And this is to implement a compute-intensive single-board computer. On the right side, we have an IO-intensive case. This is where the SBC will have video interfaces, USB interfaces, Ethernet support, expansion plane capability, and also the ability to potentially place an XMC on top of it for expanding I/O. On the left side, we have the profile for the primary switch slot profile within a system. This is 14.4.14. This is widely used, and it implements the data plane and control plane connections in a dual enclave manner. And on the right side, we've got the first use case for a GPGPU payload profile, which also uses 14.6.11. In expanding this, we have the compute intensive, which uses 14.6.11, the primary payload, which can be used for the GPGPU, or it can be used for other payloads like SDRs or transceivers or other cards. But then to ultimately expand to the highest bandwidth, we need another profile, and this is called the secondary payload profile. The benefit here, as you can see in the blue space, is that you have additional expansion plane width in the profile to be able to give you more lanes to support higher bandwidth, and we'll show that in a little more detail in a second. So the basic construct that we need to implement an AI capability is an SBC coupled to a GPGPU. And in this case, what we're showing is the IO SBC coupled with a by-4 expansion plane on the within the backplane with 4 lanes that's connected to a primary payload slot. This gives us the pairing that we need to communicate between the SBC and the GPGPU and to access the memory of the GPGPU. If we look at how could we extend this, one can scale this, and scaling can take place by concatenating the expansion plane connections across multiple slots. So in this case, we have an IO SBC. Next slot, in slot 2, we'd have a GPGPU. And then in the slot, we would have a switch that allows us to extend the expansion plane to another endpoint, which would allow us to couple 2 GPGPUs. In this case, these additional GPGPUs will look like an array of GPU capability to the SBC. And this lets one expand capability. We can also use this other slot for a payload. For instance, if you want to use a camera interface, or if you want to use a software-defined radio, you could take RF, digitize it, bring it in as INQ samples, and have it be processed by the SBC GPU pair to do INQ processing, for example. Next, we look at what do we do to scale performance. So you can scale performance in a couple of ways. One way is to increase the number of GPUs. Another way is to use a more capable GPU with a larger array of processing elements, so a larger number of cores. And to do that, though, you may have a larger amount of memory, and you need to get more information back and forth across between the SBC and the GPU itself. To do this, this is where the secondary payload profile comes into play. In this case, we have the secondary payload profile providing the interconnect for the primary single board computer. And to the right of that, we use a GPGPU with a wider PCIe data path to its device. In this case, we're scaling from 4 to 8 to up to 16 lanes and up to Gen 4 PCIe speeds to gain the highest bandwidth pipe possible. So what we're showing is a way to have flexibility by using by-4 paths to single IO SBCs, or very high performance, compute intensive, wide data interface between expansion planes, between the GPGPU and the SBC. So what does the topology look like, and what do we end up with? This diagram is in OpenVPX terms of construction, showing profiles interconnected in a hierarchy across the different data plane types that are within the architecture. If we walk this up from the bottom to the top, we have the control plane in these green blocks that implements the control plane via Ethernet. Then we have data plane in the yellow blocks that are also implemented by Ethernet, up to by-4 pipes that can give us bandwidth from 40 gig to 100 gig, depending on the switch that's being used. So here we're showing the switch associated with this area of the topology, because this is where this fabric is actually implemented. Also in the architecture, we're showing the IO SBC, 2 payload slots that are connected together and by the expansion plane, and then the wide data plane pipe here implemented to the right. Also in this backplane is a VDA62 slot that can be used for a deployment case where one needs to have a 28 volt DC plug-in power supply that's VDA62 aligned, to actually allow you to take this backplane into a deployment architecture. On the right side here is a ruggedized SAVE chassis as an example of a deployment box. So in scaling again, we can see that we can scale in the first 2 slots of the backplane by increasing the number of GPUs from 1 to 2, or we can use a more high power single board computer that's compute intensive with wide data interface to the GPU over here on slots 5 and 6. So what does a compact frame look like? This is an example of the compact frame that's AI ready. It has 6 slots plus 1 for power, internal conduction cooled slots for conduction cooled plug-in cards, internal fan cooling for cooling the cards, where we have power to dissipate on the order of maybe up to 65 watts, maybe higher. So we have somewhere between 50 and 75 through the chassis. So cooling is necessary and it's incorporated. Inboard power up to 1400 watts, test points, and then also 2 other things that are required in SOSA systems. One is the chassis manager. It's 46.11 tier 3 aligned. And then something that makes life easier is maintenance port aggregation. This is a capability within chassis that aggregates the RS-232 or LVTDL now in the case of SOSA maintenance ports from each individual PIC to one USB port that makes it easy to access the devices that you're developing with. So a few more pictures of the compact frame, test points on the top, control of things like NVMRO and zeroization through switches that are on the front panel, and then interface maintenance ports via USB, Ethernet to the chassis manager so you can get at it externally, let's say with a laptop, and then also serial port communication if you need that also to the chassis manager. So lastly, I'm showing the maintenance port aggregator here. Has a little board that's inside this chassis. This is new for Elma to be able to make life easier so you don't have to have 6 or 7 extra cables laying around to get to your maintenance ports. This helps consolidate things and streamline it. And this is an example of the chassis manager that's also embedded in the compact frame. So you're sort of ready to go relative to communications across the IPME bus for in-band and also now supporting out-of-band. So in wrapping up, AI applications aligned to SOSA make extensive use of GPUs and SBCs. We can support 25 gigs per lane to support 40 and 100 gigabit Ethernet and up to PCI Gen 4 with current VPX technology. As newer software becomes online, these platforms become modular and upgradable as technology improves, which is the goal of the SOSA and MOSA approach. High bandwidth local connections are required for effective AI processing across PICs. And we need in the platform to make it SOSA aligned, we need to address, and also for things like CMOS, we need to address chassis management at tier 3. And then lastly, expanding these things, we can add software tools such as More Explorer and System Manager applications to help flesh out the capabilities of the development environment. So to shed some more light on the GPUs, I'd like to turn it over to Chris Fedley, CTO of EIZO Rugged Solutions.
Thanks, Ken. I appreciate that. So I'm Christopher Fadley. As Ken mentioned, I'm the Chief Technology Officer here at EIZO Rugged Solutions. As Ken did a good job presenting here, we're really excited about this AI-ready backplane. So if you go to when SOSA and CMOS was really starting off, it is a difficult bridge Not only are we redefining payloads, not only are we changing architectures and focusing on Ethernet and things like that, there's a lot of things going on and a lot of different focuses. So there was a lot of focus, on making sure the radio stack was really getting further propagated in the Ethernet stack. And we were able to get different GPU complexes used within those frames. And especially at a development side, you're always wanting something earlier. So this is something that the first time really we can then have a very GPU and AI centric development platform where we have a product line that directly overlaps with its development platform and really allows end users to get familiar with these SOSA topologies and the GPU stack way more easy. It's really tabletop, can plug in and play and go from there. I know we've alluded to this in quite a few different webinars in the past, but now with the actual announcement of this product and as well as products from the EIZO side, I really think this is going to be important for the industry and various IRAD and early development platforms to show rapid iteration and utilization of those AI workloads. So with that, one of the things that EIZO recently did was announce our Blackwell line of offerings to the market segment. So Blackwell is the newest generation from NVIDIA. They come out with different architectures every few generations. Blackwell is an important one for our industry, and I'll go over that. But I just wanted to highlight, if you want more technical details about Blackwell and specifically our offerings, we've released various press releases as well as blogs about the architecture itself that you can look over. When you look at Blackwell and you compare it to previous generations of GPUs and where we were early with SOSA versus where we are now, here's a good demonstration of that. So Blackwell, as highlighted here, it is the next generation of PCIe. It has the newer memory type with 60% efficiency improvements. It has more memory available. And when you look at an architecture overall and what typically changes generation to generation, they are different priorities based on the fabrication and the different things available here. So specifically with Blackwell, and especially on our swap-C constrained embedded environment, Blackwell is very important. That memory change alone is where we typically see a lot of throttling within AI workloads. It's not typically on the number of cores and the actual performance of those cores. It's oftentimes the buses and the data ingest and the memory quantity that can restrict those payload sides. So we are really leaning in heavy on the Blackwell architecture because of those. I think it's going to be really important to really show that powerhouse performance of the GPU itself, because we can get the data in there effectively and quickly. So one of the products we announced is called a GR5S B5000. This is a successor to an existing product line we have called the GR2S, and it deploys a Blackwell B5000 GPU with the Gen 4 switch that many are familiar with from our pre-existing products. The reason we deploy these switches is really for flexibility of backplane topologies and different root endpoints, daisy chaining different endpoints like FPGAs and storage. And we wanted to make sure we preserved the exact same interface customers are pre-existing and comfortable with, and just bring the latest gen GPU to that platform. You'll see here that is a Gen 4 switch. The TRL level, as well as how robust it is and the industrial temp of it, makes it a very future-proof platform. And while we're taking this Gen 5 GPU and setting it to a Gen 4 switch, we are still offering that X16 interface and that flexible backplane topology. So when I refer to these flexible backplane topologies, here's a prime example of that. With this switch built in, you can utilize multiple GPUs, and that AI-ready backplane has 3 slots available with the IO-intensive SBCs to be able to demonstrate this performance using X4 PCIe daisy chaining. So here's an example of multiple GPUs, but it doesn't have to be multiple GPUs. You can add an FPGA, you can add storage to that endpoint, and there are certain benefits of having those endpoints directly tied to the switch next to the GPU itself, especially if you're trying to use the GPU to process that data from those endpoints. So if I'm going to load storage, having that P2P localized to that endpoint and going to direct to GPU memory will result in both read and writes faster into the GPU complex. Same goes for the FPGA and basic signal processing ingests. That said, with the other product we are announcing is really going back to basics. For years, we really serviced a 3U VPX platform that was just a GPU and no other constraints of the switches and different ICs on there. We would typically actually route the interface to all of P1 here, which is different than a lot of the SOSA models. So this product called the GR5SL, what we're really focusing on is going back to those basics, bringing something that's just pure GPU horsepower, no interruptions of the switches, and this also allows us to utilize it as a test platform for PCIe Gen 5. So PCIe Gen 5 is now here. You will see it in various SBCs from Concurrent. It is now here on the GPUs as well. With every generation of PCIe, the data rate doubles. So that includes the bandwidth, but also the latency. That said, we have to consider all parts of the PCIe pipe. So we are interconnecting through VPX connectors, backplanes, the loss on those interconnects at each point, and so on. So there is a lot of infrastructure behind the scenes that has to be iterated to support these faster generations. And this is a product in which we're able to do that. Next slide here. Looks like my picture got taken, but that's okay. This is a PCB that has the switch as well as the GPU present on here. So you can imagine there's essentially that green line there is where the GPU is. That whole complex you can essentially operate at a 50 to 150 watt ratio. And depending on what you're trying to do, you can throttle that down. But the switches adjacent to it typically can run anywhere between 20 to 30 watts. So you have to consider that this extra functionality can take away from the raw, pure GPU performance, because at the end of the day, we are in an embedded environment and we have to be able to cool these things effectively. So that 30 watts may be trivial in some environments. In others, it can be, very critical. That could flow to 15 watts or more taken away from the GPU's performance. And in some of these mission critical applications that may not be feasible. So you can see here with the switch complexes, we have an SBC. This is now demonstrating on a payload centric platform with the secondary slot profile Ken went into. And you can see we're interconnecting two of those switch cards. What the SL allows, and there's my board with my Photoshop out of the switch itself, is just the GPU complex itself. What that allows is the GPU can take that whole entire thermal and power real estate, and we can focus on our frame and making sure that the piping, chambers, all these things are built around the pure GPU performance. And can really escalate and get that raw throughput there. Keep in mind as well that just because this card may not have a switch on it does not mean that those flexible backplanes with those daisy chaining aren't still available and can't be utilized by this. So a lot of the Ice Lake Xeon D processors and the newer generations of those Xeon D SoCs have a lot of flexibility when it comes to bifurcating the CPU's PCIe complex. So your CPU will always be your root. Let's say you have X16, Concurrent offers options at a .13 secondary slot profile. It can be configured within software of the BIOS to different interlinks, depending on the SKU you're using. And therefore, I can take that same flexible backplane topology, get two separate GPUs. I'm just putting them in different slots, which again, from SOSA, this is some of the things that SOSA and MOSA philosophies unlock for us is flexibility as we iterate different generations. There are some things to mention there when it comes to P2P and RDMA and how that's routed, but keep in mind that don't immediately assume you must have this functionality. Another game changer I want to go over is multi-instance GPU. This is something that if you look at NVIDIA as a whole, it's something available in their data center stacks for a long time. And really it's bringing what you're used to with a Intel CPU virtualized complex of taking a single CPU, but virtualizing it to present as multiple different instances. In those data center GPUs, they're very large. They have lots of cores. They have 128 gigs of memory. So you can imagine if you're splitting that up, there is a lot of flexibility, but we are in a embedded space. So the multi-instance GPU accessibility we'll get on the B5000 will be stripped down to only a single split instance, meaning I can take that 24 gigs of memory, split it into, and present to the PCIe complex as two independent GPUs. And why that is important is, just for sake of conversation, let's say I have 4 GPUs tied on a bus, and maybe I'm running a container-heavy workload that needs to be more deterministic, or maybe even a VM structure where I need a clear GPU per VM, and I can't rely on different softwares or servers to be able to handle the load balancing between these. The only way you can really do that is clean separation and virtualization of the workload. So here, with MIG or without MIG, I'm going to have to put 4 physical GPUs in the system, right? Just to get those 4 truly separated deterministic instances. With MIG, I'm able to take one of those GPUs, present it as 2, and therefore still get my 4 GPUs that have these clean isolations, but I'm only using 2 of slots instead of 4 now, or I'm not having to use a single slot with multiple GPUs on it. So as you look at different workloads that are rolling out within our ecosystem to allow more faster adoption and refreshing and containerization, things like this within the GPU stack are going to be critical to make everyone's lives easier as those deploy. And like I said, those VMs themselves may not be as important one-to-one, meaning you may have a workload that is really passive, not as strict, and then I have one that may need to be very deterministic and very performance focused. Separating these GPUs this way allows a lot more flexibility there, where I'm not relying on potential software changes. I also can bind certain cores to certain GPUs and so on. And the last product we announced recently is called the GR6 AD2000. So this is an ADA GPU complex. Typically what we do is we bring the GPUs to the market segment, the raw GPU itself, and then add on over time some of the other capabilities we have within our engineering department. So this product here, you'll see, supports both the primary and secondary payload slot profiles. It can do X16, but what's different is it includes a video aperture that aligns with SOSA and VIA65's newer mantra of bringing aperture and blind mates to the segment. And this is specifically for video at 75 ohms. So we're utilizing one of these apertures. We can bring in 4 12G SDI video. We can bring it directly into the GPU memory. But it is in that 1-inch pitch conduction cooled form factor that you will see time and time again within the segment. As you can see here, essentially this involves taking a camera, going from 75 ohms and then directly into the GPU. On our side, we handle all the translation from single-ended BNC over to a differential pair on our board to be able to ingest this data. A lot of the video applications we previously would utilize would require custom circuitry within the backplane because the VPX connector itself is 50-100 ohm. So the 75 ohm is important for this, and this is something now we can offer adjacent to our traditional SDI offerings. This product also supports outputs over that same connector. So while a lot of our products are focused on compute and inputs, we can still now support rendering via SDI to various SDI monitors available to the market segment. With the AI-ready backplane, the 2 slots to the right do support this secondary slot profile and the aperture hole for this connector. So that is an exact platform to be able to support this product and be able to blind mate in and start testing a direct coax interface. So software is extremely important in all this. One of the things I really wanted to highlight was something called NVIDIA HoloScan. Over time, you'll see a lot of media pipelining. So this goes back to Direct Show and GStreamer and things like that. NVIDIA came out with their own deep stream framework that's kind of built on GStreamer. And HoloScan is now they're doubling down of coming up with an optimized digraphing and pipelining system. What they're focusing on and why they're investing a lot on this is making sure that the GPU complex itself is isolated away from the sensor, and it leans into Ethernet, which is something that SOSA is also leaning into. So the idea here is this is a software framework. They're actually enabling FPGA vendors themselves. They are opening up this framework to even expand that portfolio. And in that FPGA, you can handle all the sensor-specific conversion and then distribute it over Ethernet. And a lot of the things I've discussed in the past about Rocky V2 and RDMA, this framework takes into account and is aware of. And it doesn't have to necessarily just be Ethernet focused. You can still utilize parts of this pipeline over PCIe or USB or any type of sensor ingest. It's just when it comes to those specific sensor inputs, this is now another way to utilize that. So they're pushing a concept called HoloLink and HoloScan Bridge. These are ways in OpenIP to show how to convert radar and video and whatever type of sensor input. You have your FPGA stack to convert this, but once there, the output over Ethernet is then controlled, and they've brought RDMA to a easier to use way of interlinking, as long as then on the receiving end, it's HoloScan aware as well. So with this product, you can imagine the Ethernet-centric GPUs we provide today with a ConnectX-7 Ethernet NIC. We can take in uncompressed video data over an SDI FPGA and send it over Ethernet to a product, or any type of workload like IQ packetization and things like that. And the payload endpoint of our Ethernet-based product can ingest that data over HoloScan fast, effectively, efficiently, process it, and then in turn, send it back out as well. And all that is dropped in from NVIDIA itself. But with the newer products like the GR6 S82000, where we are doing direct PCIe capture, you can still utilize those HoloScan operators with our PCIe-based stack as well. So just because it's Ethernet focused doesn't mean you can't then drop in and take advantage of the other elements of this. We obviously will support from our PCIe and our video capture stack ability to make sure there's interoperability between HoloScan and our existing stack. And the goal really is to make this as drop-in and as easy as possible and kind of achieve what SOSA wants, which is more modularity, not just that hardware, which was the first mission, but the software side as well. With that, we also have a blog as well for HoloScan that, again, you can look at eizorugged.com for, and it kind of goes into more of those details, as well as some basic examples about HoloScan. And feel free to reach out to EIZO and kind of discuss some of the things about HoloScan, your software containerization, our future products, and things like that. So with that, I appreciate the time, and I'll hand it over to Nigel.
Thank you very much, Chris. So just very briefly about Concurrent. We're a US and UK based group that specialise in design and manufacture of these plug-in cards, some of which you've already heard about a little bit about from Ken and Chris. And we integrate those into application-ready platforms. And what I think is coming across really strongly in the webinar, or at least I hope it's coming across strongly, is that, you know, the ease that you can construct many different AI applications with the types of equipment that we're providing makes it a very straightforward and simple job and extremely flexible. So that's the thing which is most exciting to me, is that irrespective of what type of AI application you're doing, I think you should be able to find a way of actually prototyping it really well here. So looking at the sort of types of single board computer that Ken introduced and then Chris alluded to, they're required to get your AI application up and running. They're sort of the host, if you like, for the system. And I've just picked out 2 of our latest generation boards. We've got several other SOSA enabled processors, but I'm going to talk very briefly about both Hermes, which is the IO intensive board, and TRMDA, the compute intensive board. So starting with Hermes, why is that actually a good choice for some of these applications? So Chris talked quite eloquently about the variability that you need between bandwidth, between the SBC and the GPGPUs, about the amount of processing and data that you need to exchange, storage that you might want to do. So Hermes, being the IO intensive board, gives you everything in terms of flexibility. So you've got an XMC site if you want to connect additional specific IO for your application. You've got direct attached storage up to 2 terabytes on this card for for mission data or application data. It's capable of operating up to 85 degrees C card edge. So this is available for not just development in the compact frame AI ready platform, but also suitable for deployment. And you've got some other bells and whistles here. If you want to try out time sensitive networking because you want to look at moving some of those legacy interfaces to a very low latency Ethernet interface, you can do that. And a few other interesting things from the processing perspective. This particular board is based on Intel's hybrid architecture, so it has a mixture of performance and efficiency cores. So if you want to dedicate, maybe you've got a limited power budget in your system and you want to dedicate almost all of your power to the GPGPU because you've got some heavy AI crunching capability that you want to do there, you can actually scale down the processor performance by turning off some of the performance cores, or all of them potentially, and using some of the efficient cores, and actually get a very low powered SBC there. Alternatively, on the compute intensive platform, this is really designed to be much more CPU capable. So this particular board has a mix of 10 processor cores, Xeon processor cores, so they're very performant. It has 128 gigabytes of DRAM with things like total memory encryption, and it's really well optimized for this size, weight, and power capability. So very low weight card considering the performance, still available to operate up to 85 degree C card edge with some additional security capability here. So in addition to a M.2 site, we are able to give you FIPS 140-3 compliant storage on this board. And that's what I wanted to end on. So we've talked quite a bit about how you construct your AI applications. Obviously, most of the potential targets are in the defense arena. They are particularly security sensitive. And so the CPU being the root of trust very often in this type of application, I wanted to sort of talk a little bit about some of the layers and the capabilities that we provide, both as standard and also additional options that we can provide to make as secure as possible that people can't gain unauthorized access and that no IP can be either inserted or extracted from the system, right down to some fairly significant details about how physical devices are plugged into the system. If anything's changed in that configuration, we will make sure that that is detected and blocked and can stop booting the system. So there's a lot of things that we can do to enable the security of your AI application that you might want to come and talk to us about. And with that, I think there's not a lot else to say. From the SBC point of view, it's really a very straightforward platform that enables you to do a variety of different applications. And so with that, I'm going to take that to Jamie to see if there's any audience questions. Thank you.
All right. Thank you so much, Nigel. A few of you have already submitted questions, so we're going to jump right in. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. Also, please stay until the end of the presentation to complete our exit survey, which will pop up on your screen. You can preview the questions now by clicking the exit survey icon on the left side rail. So we're going to jump right into some questions now. Nigel, how reliable is AI in providing actionable intelligence?
Okay, so by its very nature, AI is inferring an answer based on a trained data model. So if you insert the same same live data into the system, you will always get the same result because it's used exactly the same algorithm it did last time. How well you've trained that AI model is entirely down to you. There are some models where there is very tightly defined data and it will always come up with the answer you think it should provide. But again, AI is very much, you get in what you get out what you put in. So it is very definitive, but it will definitely benefit from the best possible training that you can do to set the model up in the first place.
Yeah, if I could step in on that too, I think that's the critical point is people in general, they're used to AI from just ChatGPT and consumer land, right? And of course, there's a lot of hallucinations and things like that. But AI is a large term. So even when it gets to your GPU and what you're looking to select, LLMs versus videos, CNNs and things like this are all different. And a lot of times they're multimodal as well. But each one, and especially our market segment, has to be trained for specific workloads. And once you get down to that and you've really structured it, it becomes a lot like a traditional algorithm. It is static at that point. Obviously, in field, you'll get new data and different responses. But I want to be clear, when it comes to AI, it's not the same as consumer world where it's LLMs and every arbitrary question across the sun. This is highly focused, and it's an important workload to look at.
Great point. And sticking with the GPUs a bit, Chris, when will Blackwell be available?
So our focus is really those GPU-only models. We also have XMC models available. We're really pushing to get those out by end of the year. NVIDIA just released the embargo for those at GTC in March. And if you're a gamer, the 50 series really just came out end of year last year. So we've had access to designs. We've been working on our PCBs, hoping to get stuff in our labs soon here, and then be able to iterate and get to a readiness level to deploy by end of the year. Some of the other product lines when it comes to switches, obviously ConnectX-7 is important for Ethernet payloads and things like that. We want to hold off a little bit just because we want to make sure Blackwell as an architecture itself is ready for the environment we service it to.
Thank you. Ken, a question I think you might be able to address. Can payloads other than GPUs and SBCs be used in the backplane?
Yes, they can. And one of the ideas of this platform is to be able to mix other types of payloads in, where really this may be where you'll be bringing in the data that you're operating on as part of the sensor that you're constructing. So because of size, we don't have a huge extra set of payloads depending on how you're configuring your GPUs, but we have included the standard profile so that you can place at least one card next to one of the GPU constructs and take data in. So there is some flexibility here. And then ultimately, I think based on architecture that Chris has outlined, we'll probably see other variants of this coming down the road. But we really want to try to get enough capability for our customers to get sort of a sandbox available to them to start prototyping applications.
Thank you. Chris, one for you again. When do you think PCIe Gen 5 will come to the VPX market segment?
Yeah, so I think the important thing to note is, obviously I mentioned Blackwell. We're trying to get to market by end of the year. I'm sure, Nigel, you can mention some of your offerings that are starting to push Gen 5. So from a PIC level, and what I mean by that is the ICs localized on our modules, right? ICs in general, they're Gen 5 ready. It really goes back to, the RT3 connector versus RT4. All of those different elements, are existing backplanes going to be able to handle it? Are we on the edge, decibel loss, and things like that? So I would hope, those things are going to be iterated upon and be vetted, because it is important for lower latency workloads, and taking full advantage of those. Crystal ball when it comes to when that whole ecosystem together will come along. But yeah, I know, Nigel, you guys announced Kratos and other things that I think are aggressive on that as well when it comes to Gen 5, right?
Yeah, so we've announced, as you say, a Kratos product, which is based on a Xeon 6 silicon, which will be available this year. But your point about the ecosystem is really valid, because we're in a situation where, in this case, 1 + 1 + 1 = 4, because we've done a lot of work between ourselves and some other vendors as well, in terms of making sure that our products work together at 100 gig Ethernet and PCIe Gen 4. We've got to go through another cycle with PCIe Gen 5. So it being available is great, but being deployable is another thing. And we need a whole system to work together nicely to make that a realistic scenario. So it will be a little while, but we'll definitely be shipping PCIe Gen 5 capable Intel-based PICs this year.
Thank you.
I'd like to add one thing to that. So as the other gentlemen were speaking to the architectures intra-card or intra-PIC, you'll see those Gen 5 levels within those PICs will be bound by Gen 5 performance external PIC-to-PIC by the actual connector that's used in the VPX backplane and on card. However, the good news is the industry's afoot with something called VIDA 100, which is leading to the next generation protocols, Gen 5 and Gen 6. Probably within a year, we'll see the industry get to a new version of VIDA specification that will allow the ecosystem to start to address that. So good news. I mean, we've been in this realm of connectorization for nearly a decade around VPX, going from RT2 to RT3. What we see, and I've seen Steve DeVore talk about this, who's leading VIDA 100 for VIDA, how we're actually going to be able to start catching up in the rugged embedded world to address higher speed protocols with what's being done in VIDA 100, and it's pretty exciting stuff.
Oh, that's great news. Okay, Ken, question for you. Does the backplane support 100 gig switches, and what generations of PCIe are supported?
So we're, yes, able to support 100 gig, and within this team of companies that we have here today, as Nigel points out, we work together in ecosystem to try to prove these things out intra-vendor. If it doesn't work in between our different houses, it's not very useful. So it's important. This has been a challenge. We've run into things like over the years where we've pressed on how you can configure Ethernet protocol and how you can get to 100 gig from 40 gig. It's quite extensive what you need to do as far as the technology, and this has improved greatly. We've done all kinds of nifty things in industry from the concurrent point of view, where they have some of the latest devices that normalize the way that we can go from 40 gig up to 100 gig, then make that interconnection across the fabric through switches that also operate either 40G and 100G. At the end of the day, what the user wants to see is this to work seamlessly. There's a lot of SI work that goes into this, and a lot of engineering and design work to try to bring all this together with high-speed materials. And fabrication processes that we need to deliver it. So we are at the place where we can do 100 gig now Ethernet, and as we go, we continue to prove these things out to try to make sure we're covering it around the bases where we not only have to get this to work at room temperature, it's got to work across the wide temperature spectrum and across shock and vibration. So it makes it very interesting. So anyway, it's that's there. Gen 4 up to Gen 4 PCIe is there in our backplane designs today across the backplane, and then we'll be striving to look at what we got to put into R&D to get us to the next levels as we go.
Fantastic. Nigel, spinning back to AI a little bit, are all of the AI use cases you've been seeing using video recognition?
No, is the honest answer. I mean, obviously, video is one of the easiest things to visualize because you see these pictures on the TV and commercial pictures of, squares around different types of vehicles and things like that. Object recognition is an obvious application, and absolutely, we've seen video applications. We've seen electronic warfare, RF signal intelligence type applications. Chris and Ken were both mentioning a whole host of other use cases for things like SAR, software-defined radio, text-to-speech. Ken was mentioning. So absolutely, the technology is capable of any type of AI application. It's up to you to train your database and feed in the right data, and we'll do the inferencing.
Fantastic.
Yeah, that's really the side too to emphasize is it can be sensor agnostic because this is a paradigm shift of how you train and do the workload. So really anything's unlocked at that point. That's why we're seeing a lot of use of RF. Radar's an up-and-coming big one for this. As Nigel said perfectly, video is the easiest to understand because we have existing computer vision workloads. Here are the AI versions of those. Look, they run better. But really, Pandora's box is open when it comes to this can be used for all paradigms and all sensor workloads. And we've seen it time and time again do it way better than you would expect with, frankly, minimal training.
And I'll bet one of the first customers for the AI-ready compact frame uses it for some other application, AI application.
Yeah, that's the idea.
All right. We are coming up on the top of the hour. Try and squeeze in a couple of last questions here. Chris, isn't HoloScan only for the medical industry?
Yeah, good question. So we're obviously a very NVIDIA heavy house, but their branding when it comes to their software stack can be confusing because it iterates and it's adopted so quickly, right? So that's my way to play it stable like that. HoloScan did launch with a very clear singular focus on addressing the medical market. So a lot of the initial ones around Clara and other things were based around that. And then they started realizing, wait, this pipelining can be used and address a bunch of problems. It doesn't have to be medical specific sensors. So started at medical, now it's any domain. And like I said, we're pretty excited about it.
Awesome. And our last question for today's presenters. Ken, how about we go with you? Will the development platforms be available integrated with cards?
Yes, we have that in plan. We'll be offering certain reference configurations with the single board computers from Concurrent that Nigel talked about today. And also some of the GPUs that Chris talked about also. So this to make it more easy for the customer to get up and running and turnkey, really bring the other types of payloads that they need to use themselves directly into the platform, but to give you a lift to get things going.
Fantastic. And I am afraid we have run out of time, and that will conclude today's presentation. On behalf of M&AE, I would like to thank Ken, Chris, and Nigel for their fantastic presentation today, Elma Electronic for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of your day.
Thank you.
Thanks.
Yep.